So this is the last video in hypothesis testing. The first one was an introduction. It was the idea of, hey, we're creating a null hypothesis and an alternative hypothesis. And either we're going to reject the null hypothesis or say we don't have enough evidence to reject, or we're going to support the alternative hypothesis or say that there's not enough evidence to support the alternative hypothesis. And this has to do with what our claim is. We also talked about the different types of errors, or type 1 and type 2 errors. Type 2 occurring when we reject the null hypothesis but we were wrong, or type 1 occurring when we fail to reject the null hypothesis but we were wrong. Okay, so in the last two lectures, we talked about hypothesis testing for the mean, and we talked about the difference between hypothesis testing when sigma is known and when sigma is unknown. And when sigma is known, we use the z-score. I just want to clarify, I think I might have mixed up the type 1 and the type 2, so I'm going to say it again. Type 2 error is we failed to reject the null hypothesis and we were wrong. The null hypothesis is false. And type 1 is we reject the null hypothesis and the null hypothesis is actually true. Okay, I just want to clarify that just in case I said it incorrectly. But anyway, for the hypothesis testing for the mean, if sigma is known, then we use the z-test, okay? We're using z-scores. And if sigma is unknown, then we use the t-test. We're using t-values, okay? And this is the same as what we did in confidence intervals. So when we test for proportions, when we do hypothesis testing for proportions, it's the same idea. We use the z-test. That's what we used for confidence intervals. So everything that we're doing here is nothing new. It's just very repetitive. So let's take a second and talk about when these hypothesis testing for the proportions are used, okay? Let's suppose that we want to know if a candidate is likely to be reelected. That would be a case where we're doing a hypothesis test. We're claiming that, yes, our candidate will be reelected, and we're basing it on some sort of proportion of people who say they would vote for this candidate. Another time that we might use it is if we're a politician and we want to know if we should pass a bill. Is our constituency supportive of it or not supportive of it? In the time of coronavirus, you will hear a lot of the governors saying that we need state and local funding for state and local governments. And maybe the Congress, whoever is in Congress, or the senators, maybe they want to find out, okay, well, is this what the people want? So they're going to do proportions, and then they're going to do hypothesis testing. Maybe we use it for quality control. If we're a company, we want to know if it's safe to put a product on the market. So we look at the proportion of products that are defective, okay? So there are a lot of proportions that we use. So we talked about the fact that for proportions, we use binomial distributions. And remember that binomial distributions have two outcomes and two outcomes only. So it might be, yes, we're going to vote for the candidate, or no, we're not. Yes, we want you to pass the bill, or no, we don't. This particular product is defective, or it's not defective, okay? So that's when we use these population proportions. So we're looking at a binomial distribution. A reminder, two outcomes. Okay, and once again, we're using a z-test. So we need to see if this binomial distribution approximates a normal distribution. And we test for that. should say approximate. And in confidence intervals, we used NP hat and NQ hat, and we said that they needed to be greater than or equal to 5. Here, if you remember, we're not using the sample, okay? We're using the actual population parameter, okay? Because what we're doing is we're making an assumption. We're assuming that the null hypothesis is true. And the null hypothesis is a hypothesis about the population, okay? So this means that instead of looking at NP hat, we look at NP and NQ. So NP must be greater than or equal to 5, and NQ has to be greater than or equal to 5, okay? We also know that when this is true, the mean population proportion for the sample is the mean sample proportion is equal to the population proportion. And the standard error is the square root of PQ over N, okay? Again, we refer to it as the standard error. So we can use this to find the z-score, okay? So the test statistic that we're using, remember we need a test statistic and then we need to standardize it. So the test statistic is your sample proportion, and sometimes that's going to be given to you. If it's not, then it's X over N. So remember, this is the number of successes over the sample size. And we're going to be doing some where this is given to you and some where you have to actually calculate it. And then the standardized test statistic is your z-score. It approximates a normal distribution, not a t-distribution, so we use the z-score. So it's the sample proportion minus the assumed population proportion, okay? This is P hat. I don't know why that didn't. P hat. And then over the standard error. What does this mean? It's your sample proportion minus the population proportion from the null hypothesis over the square root of PQ over N. Okay, remember this is the number of standard deviations from the mean. Okay, so we're saying that the mean is the population proportion, and this is the standard deviation of the population proportions of that sampling distribution, which is PQ over N, and you take the square root, okay? Okay, so how do we apply this? We've done this before, okay? Nothing is changing. It's the same thing. We're using a z-test. We're going to write out the steps. So our hypothesis tests are referred to as z-tests or t-tests. This is a z-test. So we're just being a little bit more specific here. So for population proportion, Okay, and once again, we're using critical regions. Okay, so instead of finding p-values, which we did for sigma known, okay, we're going to find the critical region and see if we wind up in that critical region. That critical region is also referred to as a rejection region. And if we wind up in the rejection region, that tells us reject your null hypothesis, okay? So our first step is to verify that it's a random sample and that we have approximately a normal distribution. In other words, the population is normally distributed. I'm not even going to say population. I'm going to say that it approximates a normal distribution, because here that makes more sense. Okay. And here it's not that it's told to us. It's not. We have to find it. We have to calculate it. We have to say, okay, either both NP is greater than or equal to 5 and NQ is greater than or equal to 5. Okay, and again, we're not using P hat and Q hat. We're using P and Q because we're making this assumption that the null hypothesis is true. And then if we see that, okay, yes, it is true, then we fail to reject it. Okay. Second thing that we do is we state our null and our alternative hypothesis and identify the claim. So null hypothesis, this should be very familiar to you at this point, is H sub 0 or H naught. The alternative hypothesis again, should be familiar, is H sub A. And we want to identify the claim. Which one of these is the claim that's being made? Okay, now we're going to specify the level of significance. We've done this. We're going to determine the critical value. That's our Z sub C. And I'll call it the rejection region, because this is where we will reject the null hypothesis. Finally, you have to find the standardized test statistic. So that is your Z sub C. No, that's just your Z, your rejection region. Your critical value is Z sub C. And finally, you're going to make a decision. Do you reject or fail to reject? And a conclusion about the claim. So what does this mean about your claim? And we'll do a bunch of examples, but before we do that, once again, I'm going to put it in this lecture as well. I'm going to put in that chart where we have how do we make a decision about the claim, right? So we have our claim, and either the null hypothesis is the claim, or the alternative hypothesis is the claim. We've said this 4 times, I think, in all 4 lectures. And then we have our decision. So we're either going to reject the null hypothesis, because it's all based on the null hypothesis, or we're going to fail to reject our null hypothesis. So depending upon the claim, we could either support the claim, or we could just say that we reject it or fail to reject it. So if we reject the null hypothesis, and the null hypothesis was the claim, then what we're doing is we're rejecting our claim. We're saying, nope, it's wrong. If we fail to reject the null hypothesis and the null hypothesis is our claim, then all we're doing is we're saying we don't have enough evidence to reject the claim. We're not saying, okay, we are not saying that we're not saying that the claim is right. We're just saying we don't know. I just essentially wrote the same thing. We're saying that there's not enough evidence to reject the claim. Okay, we don't know if it's right or wrong. Now, if we reject the null hypothesis and our alternative hypothesis is the claim, then we're supporting the claim. We're saying it's right. And if we fail to reject the null hypothesis, we're not saying that the claim is wrong. We are just saying that there's not enough evidence to say it's right. Not enough evidence to say either way. So if you want to support a claim, that claim has to be the alternative hypothesis. If you want to say, yes, you're right, then that claim has to be made into an alternative hypothesis, okay? And if you want to say someone is wrong, the only way to be able to do that is if their claim is the null hypothesis, okay? So let's just go through a bunch of examples like we've done in the other lectures, okay? So I apologize for all of the writing. There's not really a way around it. So let's say that a researcher claims that less than 45% of U.S. adults use passwords that are less secure because difficult ones are hard to remember. you're going to do a random sample. So you have a random sample of 100 adults. And we're saying US adults. So keep in mind that we're very specific here, okay? Because we have to be. You can't just take any adults, right? Because our claim is about US adults. So we have to take a random sample of 100 adults. And in that random sample, 41% say they use, not just that they use less secure passwords, but that they use less secure passwords because difficult ones are hard to remember. Okay, and what you want to do is you want to say, okay, at a level of significance, if you remember, the level of significance is the probability that your sample proportion, okay, the probability that your sample proportion is an anomaly, okay? So at a level of significance of alpha, that's how we represent level of significance, is equal to 0.01. You're saying, is there enough evidence to support the researcher's claim? Okay, so you're saying that your sample proportion is occurring less than 1% of the time. Then you would reject the null hypothesis. Okay. Okay, so let's go through the different parts of this. So we're just going to go through this checklist. Okay. The one we have to verify. Then we're going to state our hypotheses. Then we're going to specify the level of significance, which is given to us. We're going to determine the critical value in the rejection region, okay, which we've already calculated for a lot of these levels of significance. Then we find the standardized test statistic. We use this. And then finally, we make a decision and a conclusion. So let's do the verification first, okay? So we have to verify that it approximates a normal distribution. So we need NP and NQ to both be greater than or equal to 5. Okay, so before we do that, let's just make sure that it's clear what P is. So P is 0.45. P is what is the claim, okay? It's our hypothesis. So P is 0.45. So that means, in other words, it's not this 0.41. That would be P hat, okay? That's from the sample. It's this that we want. So P is equal to 0.45, and Q is just 1 minus that. So it's 0.55. So NP is equal to 100, because that's what N is. I'll put that in here. N equals 100. Okay, that's given to us. That's our sample size in a random sample of 100 US adults. So NP is 100 times 0.45. That's equal to 45. So that is greater than or equal to 5. So check for that. Then we have NQ. So that's 100 times 0.55, which is 55. And that's also greater than or equal to 5. So check for that. Okay, so this does approximate a normal distribution. Okay. 2, we have to state the null hypothesis and the alternative hypothesis. So the null hypothesis is H sub 0. Alternative hypothesis is H sub A. Okay. Again, the way that I typically do this is I go to the claim and I use that to help me figure out which is which. So the claim says that it's less than 45%, so less than 0.45. Okay. So if we're doing that, less than is an alternative hypothesis. So we would say that P is less than 0.45, which means that the null hypothesis is greater than or equal to. That's the opposite. So keep in mind, that the null hypothesis includes the equals. The alternative hypothesis does not. Okay? And H sub A is your claim. So now we have to specify the level of significance that's given to us. This is a nice, easy step. Level of significance is just 0.01. Okay. We need to go in and we need to find our critical region. So our critical region, what we do is we go into the z-score chart and we're looking for 0.01. Okay. So it's going to be here. It's less than a half, so it's going to be in the negatives. 0.0107, I'm going to go back, 0.0104, 0.0102, 0.099 is the closest, okay? So what's the z-score there? Negative 2.33, okay? That's our z-score. That's our critical score. Okay, so how did we get that? We looked for 0.01 in the chart. Okay, now we have to figure out the region. Well, this is remember, to figure out the regions, you have to figure out, is it a left-tailed test, a right-tailed test, or a two-tailed test? This is a left-tailed test. So left-tailed test means that we're looking for the region that's to the left of the critical z-score, okay? So left-tailed test it's left-tailed because H sub A has a less than sign. Okay, if it has greater than it, it's right-tailed. If it's not equal to, it's two-tailed. So this is a left-tailed test, which means that our critical region is Z. Our standardized test statistic has to be less than negative 2.33. Okay, this is our rejection region. In other words, if our z-score is less than negative 2.33, then we reject the null hypothesis. Okay, so the next thing that we have to do is actually figure out the standardized test statistic. So this is p hat minus p over the square root of pq over n. So p hat is given to us. We don't have to calculate it. It's a proportion that's given. 41% is a proportion. So p hat is 0.41. P is the 0.45 that we were given. And then we're dividing by the square root of 0.45 times 0.55 over 100, because that's our sample size. Okay, practice putting this into your calculator. So do the 0.41 minus 0.45 first. If you're using like a graphing calculator, you can do it all at once. You could put it in parentheses and then divide by the square root and puts what is in the square root in parentheses, okay? Or just do it in small bits. Do it in small steps. Do 0.41 minus 0.45. Do 0.45 times 0.55, divide by 100, then take the square root, and then take the 0.41 minus 0.45 divided by that answer. So practice putting it into your calculator. This gives you negative 0.80. Okay, and I'm going to warn you against rounding too much. Okay, really try and take as much of that number that you get as possible. I would even go as far as 3 decimal places sometimes, because it can make a big difference. Okay, and then the last thing that we do is we figure out, do we reject it or do we fail to reject? So we're looking to see, is negative 0.80 in the rejection region? Negative 0.80 is not less than negative 2.33. It's not in the rejection region. So we fail to reject the null hypothesis. Okay, this slash through the less than sign is saying it's not in the rejection region. Okay. Now, what does this mean about the claim? It's saying there's not enough evidence to support the claim. We can't say that the researcher is right. We can't say the researcher is wrong, but we certainly can't say that the researcher is right. So we can't say that less than 45% of US adults use passwords that are less secure because the difficult ones are hard to remember. We can't say, okay? We're not saying that they're wrong, okay? Okay, let's take another example. Let's say that a researcher, I'm going to do this in black so that we don't confuse our questions with our answers. So a researcher claims that more than 90% of US adults have access to a smartphone. So we're going to take a random sample. It's going to include 150 US adults, and 87% say they have access. So now we're going to use a level of significance of 0.05. And we want to know, is there enough evidence to support the claim? So once again, our first step is always to verify. We have to verify, is this binomial distribution approximating a normal distribution? Okay, this is our verification. So in order to do that, we're going to identify our N and our P and our Q. So our N is 150, that's our sample size. Our P, remember, unlike confidence intervals, we're using what's in the claim. We're using what's in the hypothesis. Okay, so our P is 0.9, which means that our Q is 1 minus P, or 0.1. Okay, so we're going to do our verification. We're going to see if NP is greater than or equal to 5. So 150 times 0.9 is 135. So yeah, this is greater than or equal to 5. But that's not enough. We also have to do NQ. So we're doing 150 times 0.1. This is equal to 15, but that's okay that it's small. It's still greater than or equal to 5. So we verified. We're okay there. Now we have to state our hypotheses. So we have our null hypothesis, and we have our alternative hypothesis. This says more than 90%. So more than is an alternative hypothesis. So we're saying that P is greater than 0.9. And then the opposite of that is less than or equal to 0.1, which is, less than or equal to 0.9. Okay? Which one is the claim? The alternative hypothesis. Okay, now we're just going to identify the level of significance that's given to us. Level of significance is 0.05. And now we're going to do our z-score. Okay, so this means that we're going to go into our z-score chart and we're looking for 0.05. So 0.05 is going to be in here, okay? Looking here, 0.05, this is 0.0505, and this is 0.0495. So we're exactly between negative 1.6 and negative 1.64 and negative 1.65. So what we do is we go exactly in the middle. Okay, so all you have to do is take the lower number and then just put a 5 after it, okay, because that would be exactly what's between negative 1.64 and negative 1.65. So that means that our critical z value is negative 1.645. Okay, and we need the rejection region. So in order to do the rejection region, we need to know, is this right-tailed or is this left-tailed? So this is a right-tailed test. Okay, we know that it's a right-tailed test because H sub A has a greater than sign. So we figure out what kind of test based on our alternative hypothesis. Okay, it has a greater than sign, so it's a right-tailed test, which means that our critical region or our rejection region would be that z is greater than negative 1.645. Okay. Now we have to find our z-score. So this is our p hat minus p over the square root of pq over n. So p hat is given to us. We don't need to calculate it. The proportion is already there. So it's 0.87 over the square root. P is 0.9. Q is 0.1. And our sample size is 150. So what does this give us? Negative. Sorry, I should have put this in here, minus 0.9. Okay. So this gives us negative 1.2. Okay, now we have to figure out whether it's in the rejection region. So negative 1.2 is greater than negative 1.645. So we are in the rejection region, okay? Since negative 1.2 is greater than negative 1.645, we're in the rejection region. And that means that we reject the null hypothesis. And you can see that if we reject the null hypothesis and the alternative hypothesis is our claim, then we are saying the alternative hypothesis is correct. Okay? So we're saying we support the claim. More than 90% of the population of US adults have access to a smartphone. Okay, let's do another one. We'll do two more. Okay, so in the next one says a researcher claims 51% of US adults believe antibiotics are effective against viruses. And this doesn't have anything to do with our calculations, but you should know that this is not true, okay? Antibiotics are not effective against viruses, okay? So in a random sample, of 2,202 adults, 1,161 say antibiotics are effective. Antibiotics are only effective against something that's bacterial, not against something that's viral. So in this case, we're saying at a level of significance that's equal to 0.10, is there enough evidence to support the claim? Okay, which is what we're asking in every hypothesis test. Do we support the claim? Excuse me, do we reject the claim? Okay. Okay. So let's go through each of the steps once again. We need to make sure that it approximates a normal distribution. So our n is 2,202. Our p is given to us as 0.51. And our q is 1 minus 0.51. So it's 0.49. Okay. N times p, this is our verification. We need this to be greater than or equal to 5. So this is a little bit more than half of 2,202. So yes, it will definitely be greater than or equal to 5. And n times q is also going to be much greater than 5. So yes, we have verified. It does approximate a normal distribution. Now we need our hypotheses. So the claim is that 51% of US adults, it doesn't say less than, it doesn't say more than, it says 51%, okay? So that means that P is equal to 0.51. Okay, means equals. So that's the equals tells us it's in the null hypothesis, and the opposite is not equal to. Okay, and we did the claim first. This is the claim, H sub 0. Okay. Next, our level of significance, we just specify. It's 0.10. Okay, now we have to find our critical z-score. Now this is a two-tailed test, okay? Now here's the difference with a two-tailed test. A two-tailed test says 10% of the area is on the outside, okay? So keep in mind, you have a region that's on the inside. This is your negative z, and this is your positive z, okay? And each of these is half of alpha. The alpha is the area under both regions together. So in order to figure out z sub c, we have to take alpha and divide by 2, which is 0.05. And now we go to our z-score, and we have a negative critical value of negative 1.645. And that comes from the last one, okay? The last one, we also had an alpha that was equal to 0.05. So if you go into the z-score, we know it's negative 1.645. And then we have positive 2, so we just take the positive value. Okay. What does this mean our rejection region is? We have two pieces to it, okay? Either our z-score is less than negative 1.645, or our z-score is greater than positive 1.645. Okay, so either it's in this area on the left or in that area on the right. Okay, so we have two rejection regions. So our extra step is we have to take the level of significance and divide by 2, okay? Because the level of significance gives us the total area outside this middle region, and we only want the area on the left, okay? That's because when we go to the z-score chart, it only gives us areas to the left of things, okay? Okay, so now we need to find the actual z-score, but in order to find the z-score, we need p hat, and it wasn't given to us. Okay, All they gave us is the number of successes and the sample size. So p hat we have to calculate. And this I would guard against rounding too much, because okay, round it, don't round it if you can. Okay, if you have to round it, then take it as far as you can. So like 3 decimal places, not 2. Okay, and this is a case where if you round it to 2 decimal places instead of 3, you're actually going to come to the wrong conclusion. Okay, so it's not that I would take off so many points for something like that, but it's good to know that if you round too much, sometimes your answer could be so different that it changes your conclusion. And I'll show you what we mean, okay? So if we calculate our z-score, it's p hat minus p over the square root of pq over n. So this is 0.527 minus 0.51 over the square root of 0.51 times 0.49 over 2202. And what we get here is 1.60. So what's interesting is, and you could see this on your calculators, if we had rounded this to 0.53, we would have gotten 1.87, okay? Now, if we go to the next piece, which is to figure out, do we reject or fail to reject? 1.6 is less than 1.645, okay? In other words, I should write it like this: 1.6 is not greater than 1.645. 1.6 is clearly not less than negative 1.645. It's outside the rejection region. But if you had rounded p hats to 0.53, you would have gotten I think you get like 1.82, and 1.82 would be in the rejection region. So in some rare cases that could happen, so you have to be careful. And that's why I say, if you're figuring out p hat yourself, then go as many decimal places that you can. So even go to 4 decimal places, okay? But don't try not to round. Certainly go to the first 3, okay? So what does this mean? It means we fail to reject our null hypothesis. If we fail to reject the null hypothesis is our claim, okay? So we're failing to reject our claim. There's not enough evidence to reject the claim that 51% of US adults believe that antibiotics are effective against viruses. We're not saying that they're right. We're not saying that it is 51%. All we're saying is we don't know. And I realized that up at the top here, I wrote R effect, but it's effective. So I'll add that in here just so I don't confuse you. Are effective against viruses. Okay. Let's do one last one just so that you get the hang of it. Okay. So a researcher claims, notice all of these are about research. 67% of US adults believe doctors overprescribe on antibiotics. So in a random sample of 1,768 U.S. adults, 1,150 of them say that doctors prescribe too much antibiotics. And we're saying at a level of significance of 0.10, is there enough evidence to support the claim? Okay, so we just go through the process again. Same process every time. Okay. So our N is 1,768. That's the number of people who we asked. That's our random sample. Our P is 0.67. And our Q is 1 minus 0.67, or 0.33. So we have to verify that N times P, or 1,768 times 0.67, is greater than or equal to 5. So this gives us 1184.56. And you'll notice that in a lot of these, our sample size is so large that, yeah, you're going to find that N times P is greater than or equal to 5 by a lot. Same thing here. N times Q is going to be much greater than 5. It's only in very small sample sizes that it's going to be questionable. So if they had said in a random sample of 10 U.S. adults, then this is going to be more questionable. Okay, so the larger the sample size, the better. Then we identify our null hypothesis and our alternative hypothesis. So here it says a researcher claims 67%. There's no more than, there's no less than, so it's an equals, okay, which means that that's our null hypothesis. So P is equal to 0.67. Notice it's always a decimal. And that means that the alternative hypothesis is that it's not equal to that. And the null hypothesis was our claim. Now we specify our level of significance, which is 0.10. And we have to figure out our critical region. So this is a two-tailed test because its H sub A has a not equals to. Okay, which means that we have to take our 0.10 and divide by 2. This gives us 2 z-scores. It gives us a negative z sub c of negative 1.645. We just found this in our z-score chart. And a positive z sub c of positive 1.645. It's symmetrical about the mean. Okay. And what does this mean? This means our critical region is either z is less than negative 1.645 or z is greater than positive 1.645. That's the rejection region. So if either of those is true, then we're rejecting. Now we have to find the z-score, but in order to do that, we have to find p hat, right? And p hat isn't given to us directly. We have to calculate it. So the number of Successes, or the number of people who said they believe doctors prescribe too much antibiotics, is 1,150. The sample size is 1,768, and this is 0.650. So we're going to use this to find the z-score. Z-score is p hat minus p over the square root of p q over n. And we know what this is equal to. 0.65 minus 0.67 over the square root. Here we have 0.67 times 0.33. We're dividing by 1,768. And this gives us negative 1.79. Okay, so now we make our decision. Well, negative 1.79 is less than negative 1.645. Z is in the rejection region. So we reject the null hypothesis. Now, what does this mean? Well, our claim was the null hypothesis. So if we reject the null hypothesis, then we're rejecting our claim. We're saying it's not true. That's 67%. Okay, this is not true. That's wrong. Now, keep in mind that we're saying it's wrong, but that doesn't mean that the number isn't 62%. It doesn't mean that it's not 68%. We're just saying it's definitely not 67%, assuming we haven't made an error, right? So we talked about these type 1 and type 2 errors. So it's possible that we made an error. We have to keep in mind that we could have made a type 1 or a type 2 error, right? So here, if we're wrong and we rejected the claim when we shouldn't have, rejecting a null hypothesis when the null hypothesis is true is a type 1 error, okay? So type 2 would be if we don't reject it and it's false. Okay, rejecting it and it's true is type 1. So this would be a type 1 error if we did it wrong. Okay, so we're not saying that we're incapable of making an error. It's possible that it's a type 1 error, but if we didn't make an error, then this is wrong. 67% of U.S. adults believe that doctors prescribe too much antibiotics. So I'm going to put in here, assuming, just to remind you that it is possible to make an error. So you should always keep those errors in mind, okay? So this is a type 1 error, if we made that error. Okay, and that's it. And that's it for hypothesis testing. So this is the last lecture in the unit. So hopefully at this point, you're feeling pretty comfortable and you're seeing that it's very, very repetitive. Okay, but you do always, in all of these, you have to know what kind of test, whether it's right-tailed, two-tailed, or left-tailed, and that's determined by the alternative hypothesis. Okay, and now you should be capable of making all sorts of conclusions about research. Okay, that's it. Again, it may take me a second to pause the tape, so you could stop listening right now and ignore the fact that I keep saying tape, because that is embarrassing.